Okay, last time we were discussing a little about atomic structure, so that we could go ahead and do the valence bond treatment and the molecular orbital theory for formation of compounds, right? Now, I want to again remind you to go back and register on Edmodo, because that group remains unlocked only for a period of 1 week. After which it gets logged, and I'll need to generate a fresh code for all of you. So go and register yourself. I have uploaded one more document there, so when you go back home you can check your folders. The document folder, there is a note on valence bond theory. So whatever part I will be taking in the first few lectures, as a note it's there, you can refer to that. And there are a few books which are available in the library, but I'll talk about that a little later. So just be with me till then, and then for further reading I'll be giving you other material that you can go down and collect from the library. Is that clear? Okay, a little bit about what some of you must have seen on Edmodo about the animations, wherein the few atomic orbitals were given. If you pressed on that link, they gave you some modes of vibration, right? So those drum vibrations are what you need to visualize when you look at the shapes of the orbitals. That was the idea behind showing you those animations, because though we technically write a p orbital to be dumbbell shaped like this, what this exactly signifies is that one of the lobe has a mode of vibration which is signified by a positive sign to the wave function, and the other lobe contains the negative sign to the wave function. And what you see right at the middle here is called as a node, and it is called as a node because there is zero probability of finding the electron at the center. Is that clear? So whenever you write a lobe of a p orbital like this, don't try to picture in your mind that the electron is just in this area which is looking like a dumbbell, right? What this just means is that, like you saw the drum, if one of the sides of the drum is having a crest, the other side simultaneously is going to be a trough, and so there is going to be a vibration like this. So even though the electron is present somewhere around the nucleus, they will be vibrating in such a fashion that this part, one side will be a crest and the other one will be a trough. So a full wavelength will be formed in that particular region where you are probing the possibility of finding the electron. Is that clear? So when you write a p orbital just as this, it does not make any sense, because this doesn't mean that the electron is either orbiting in a dumbbell shape or the electron is present only in these two regions. When will this notation make sense? When you start putting the signs of the wave function and you call one of the sign as plus and the other one as minus. Note again that this plus and minus is not the charge, because the electron cannot be positively charged, right? These plus and minuses are just going to signify, when you draw a simple sinusoidal wave like this, you have something called as a crest and something called as a trough. And you always designate the crest to be the positive part of the wave function and the trough to be a negative part of the wave function. And you will always get a node, that means a point where the amplitude is going to be 0. And that node is represented in a p orbital by this that you see here, right? Another thing that I want you to appreciate is that when you saw the s orbital, the 1s orbital looked circular like this, with the vibrations happening like this. So simultaneously all of it will go into the crest, all of it will go down into a trough. So there is no node as such. But you also must have seen 2s, 3s, 4s and 5s orbitals, right? And you do see that progressively the s orbital also tends to develop a node. So please remove that concept from your head that the s orbital will not contain a node at all. Okay? There are two different types of nodes which are found in an atomic structure. When you look at an electron, the electron can have a node like this. These nodes are called as planar nodes. Why is it called a planar node? If I cut these two lobes in a plane that is projected towards you, you will see that there is zero probability of finding the electron in the entire plane. That's why I call this as a planar node. Okay? But there are also other types of nodes called as radial nodes. What do you mean by a radial node? Say for example, I take a pen, okay, I take this chalk, tie a thread to it, and the thread is extended outwards, and make a circle. I'm sure all of you must have done that. So when you make a circle, at each and every point of the circle, there will be zero probability of finding the electron. So you call such kind of nodes as radial nodes, whereas nodes like these are called as planar nodes. Do you follow that? And there is a formula to tell you how many radial nodes are present in a particular orbital. It corresponds to n minus L minus 1. Okay? So when you take the 1s orbital, the value for n in a 1s orbital is 1. Okay. Well, how do you get the value of n? It is the coefficient to any orbital. For a 2p orbital, n is equal to 2. For a 3d orbital, n is equal to 3, and so on and so forth, right? So the value of n for 1s orbital is 1. The value for L, which is the azimuthal quantum number, depends on the orbital itself. Since we are talking about an s orbital, the value is 0. So it becomes 1 minus 0 minus 1. That happens to be 0, and therefore your 1s orbital does not contain any node at all. And you get a continuous wave function. There is probability of finding the electron everywhere inside. Do you follow that? But as soon as you move to the 2s level, for the 2s level, n happens to be 2. L continues to be 0 because I am talking about the s orbital. And you subtract 1 from this, you get 1 radial node. You get 1 radial node. So how is the 2s orbital going to look? It's not going to look like that. It's going to look somewhat like this. So what exactly is happening? You see a point over here where there is 0 probability of finding the electron, and that is not a planar node, it is a radial node. You take your pen here, keep it at a fixed distance, and if you draw a circle, you will see that there is 0 probability of finding the electron here. So there is probability of finding the electron everywhere inside and everywhere outside, but not at this point. So that is what you call as a radial node. So today when you go back, again look at all the vibrations and try to identify that as you go ahead to 2D, 3D, 4D, etc., you will see that the number of radial nodes go on increasing according to this formula n minus L minus 1. Is that clear? So that is the picture I want you to keep when you look at electrons in a bound state in the presence of a nucleus in an atom. Okay. Okay, coming back to now assuming that we are moving quite forward, we've already discussed a little bit about the atomic structure. Moving on to a molecular structure, the structure that we will be discussing when we do valence bond theory will be a molecule of hydrogen. Okay. Now remember that all of you must have come across this when you did atomic structure, that the wave functions could be accurately determined only for a 1 electron system. It failed for the nearest next analog which contained two electrons, because there were so many factors which were involved, electron-electron repulsion, electron-proton attraction, and so on and so forth, that we couldn't exactly guess what the wave function could be. And hence there needed to be approximations that need to be made. Okay? So for a 1 electron system, that means for a hydrogen atom, everything is exactly known. All the wave functions are exactly known for this system, which contains only 1 proton and 1 electron. In fact, if you go online, you will see the exact wave function that is associated with the 1s orbital, the exact wave function associated with the 2p wave orbital, and so on and so forth. The exact wave function is known. It is a function of the cosine of the theta and so on and so forth. All that is exactly known for 1 electron system. But as soon as we go to the nearest analog, that is helium, which contains 2 electrons, everything fails. Okay? Why? Because we have so many interactions between the 2 electrons, between the electrons and the protons, that we can't reasonably guess what the wave function could be. And therefore we need some approximate methods. Okay? So one of the approximate methods that we will be using for H2, we'll need approximations for H2 as well. Why is that? Because you have a nucleus of one of the hydrogen atoms. Let me just label it as HA. Not that this hydrogen has something special, but just to label it, I'm labeling it as HA. There is another nucleus HB. So there are 2 nuclei. There is 1 electron corresponding to HA and 1 electron corresponding to HB. Let me just label it as E2. So suddenly the complexity is increasing so much. You saw that just with 1 nucleus of 2 protons and 2 electrons, everything failed. We couldn't guess what the wave function could be and needed some approximate methods. Similarly, as we go to 2 proton, 2 electron system, we will again need some approximations to be brought in. We don't know exactly what the wave function looks like. Okay? So we will need some approximations to come in, and one of the approximation methods is called as the variation principle. Okay? Now what exactly does this variation principle tell you? Even though I can't guess what is the exact wave function, that doesn't mean that there is no exact wave function. Are you with me there? What I'm trying to tell you is that there is an exact wave function, but what we can't do is we can't calculate the wave function with our knowledge of the repulsive and the attractive forces. So that means there definitely is a psi corresponding to H2. But since I can't guess this, what do? I break this psi up into multiple functions which I reasonably know of. What are the functions that I know of? I know that this E1 is going to face some attractive force with this HA. I know that this E2 is going to face some attractive force with HB, and I will try to add these things up. Are you following what I'm trying to say? So what am I going to assume? That this wave function associated with this electron in the presence of this nucleus, say for example I call it psi1, okay? And this electron, when it is in combination with this proton, I call it psi2, and so on and so forth. So what am I doing? I'm breaking up a complex wave function into multiple parts, so that I can approximate the final wave function. That doesn't mean that a final wave function does not exist. It very much exists, but to calculate it is difficult because it is multifactorial, and hence we need to break it up into simpler parts. And therefore we will be looking at different wave functions corresponding to different interactions. There will also be a wave function for repulsive interaction between the two electrons. But can we look at all of it together at once? We can't. So far we've not been able to do that. So what do? We look at bits and pieces of these wave functions and try to put them together and try to see if it matches with an experimental data. What is the experimental data available to you? When I take an H2 molecule and then I subject it to thermolysis, photolysis, etc., the bond energy associated with a hydrogen-hydrogen bond is very specific. That means you can only break a hydrogen-hydrogen bond if you provide it with so much energy. It is known to us, we call that as the bond dissociation energy. So it's obvious that when the bond is forming, at that time there must be release of that much energy. So we'll need to account for that much energy of the bond using all these wave functions that we devise for the molecule. If say for example all the wave functions psi is equal to psi1 plus psi2 plus so on and so forth gives me a value for E, we'll come to how we get the value for E, which is the total energy of the molecule. If that E corresponds to the energy that is stored in a hydrogen-hydrogen bond, then we can say that this approximation is reasonably accurate. Till then we can't say this approximation is accurate. Do you understand what I'm trying to say? Okay, we need to go on adding the energies and see whether the calculated energy, which is called as the theoretical energy of the molecule, corresponds with the experimentally observed value for the energy. Not only that, but also experimentally observed value for the bond length. Okay, there is a particular specific bond length associated with hydrogen-hydrogen bond, so we need to correlate both of them. If both of them is correlated, that means our approximation of the wave function is reasonably accurate, and that can be said as the wave function of the electron in the molecule. Is that clear? So that is what we'll be doing in valence bond theory. Say for example, if I plot a function of potential energy against the internuclear distance. This R is the internuclear distance. What do you mean by the internuclear distance? You have hydrogen and hydrogen. So one nucleus, another nucleus. Say they are infinite distance apart. So you will get some value for potential energy. As you start bringing them closer, what should happen to the potential energy? Why should it decrease? Is bond formation favorable? Bond formation is not favorable. If you have a hydrogen atom and a hydrogen atom, they will not come together and form a hydrogen molecule. It is favorable, and therefore it should happen with a decrease in potential energy. How exactly can you picture that? You have hydrogen which has one electron. One electron systems are not stable. When you bring two hydrogen nuclei closer, there will be some attractive force between. Again, I'm using this only for picturization. Please again don't try to keep it in your head that the electron is orbiting around the nucleus. I'm just trying to use it for notational purpose. Okay. So when they were both infinite distance apart, there will be some attractive force between the electron and the proton. But as you start bringing the second nucleus together, this electron can also be attracted to this proton here. And attraction is favorable. It is going to lead to a drop in energy. Okay. At the same time, this electron over here will also be attracted to the nucleus of the other proton, right? And because of such attractive forces, they are going to stabilize the system, and stabilizing the system means minimizing the energy. So at infinite distance, the energy is 0. As you start bringing them closer, you will see that they are going to come to an energy minima. Once the energy minima is obtained, there is going to be a sharp increase in potential energy as you try to bring the two nuclei closer together. Can you tell me why? I start bringing the two nuclei together, the energy is dropping till it reaches a minima. Once the minima is obtained, you try to compress the bond further. The potential energy shoots up as you decrease the internuclear distance further. Why does that happen? Of course, there is repulsion between the two protons, which is going to come into the picture as the two nuclei come together. At the same time, there will be electron-electron repulsions. So you will always get an equilibrium position where the energy is the minimum, okay? And that minimum energy corresponds to the bond length. Let me just mention it as R0. So this R0 will be your bond length for the two atoms coming together and forming a molecule, and it will correspond to the minimum energy of the system. Is that absolutely clear? So that is how your molecule is designed when it comes to energy as well as for the bond lengths. Is that clear? Coming back to the wave function psi. Now, since we are approximating, there will be a psi that will be associated with HA. Now, again, remember that I have two hydrogen atoms, and I'm just, for the sake of simplicity, labeling them as HA and HB. Both the hydrogens are not different at all. They are in fact exactly the same. But just for notational purpose, so that it's easy to identify, I will associate one of the hydrogens with the alphabet A and associate the other one with the alphabet B. And it's obvious that the electron associated with A, let me label it as 1, okay? And the electron associated with B, let me label it as 2. Let me use a simpler notation so that it's easy. Okay? Electrons will get the designation 1 and 2, right? Now, since I just told you that for an electron that is present around the nucleus, for a hydrogen atom, the wave function is accurately known to us, right? What we don't know is the wave function of an electron that is present in a hydrogen molecule, right? So, let me start with the wave function that's already known. What is the wave function already known? I know psi HA, which is associated with electron 1. This is already known to me. And I also know another wave function psi HB associated with the electron 2. I know both these wave functions accurately. They have been calculated. Everything is known about the two of them. So when I apply the variation principle, what do I assume? Let me just say that these two wave functions are interacting with one another, which is very logical. When you have two waves and you try to, all of you have gone to Marine Drive? Obviously, now it's been 1 year. That's such a ridiculous question to ask, right? So you see that when two waves come together, there is some interference between the waves. And that wave can either constructively interfere with one another or it can destructively interfere with one another. Is that right? So whenever I am assuming two waves are coming together, there is always going to be a summation. There is going to be an additive effect of the two wave functions together. And that additive effect can either lead to So I can just approximate the two wave functions to come together and to add up in a particular fashion. And once they add up, they should be a reasonably approximate picture of how the wave function of the molecule is. Now this is an approximation, right? Because I'm not trying to find out the psi for H2. I'm trying to approximate that the total psi must be some addition of the psi for hydrogen A and psi for hydrogen B. Is that clear? So we've embarked into our journey of variation principle actually. Is that clear? Now remember that this psi tells us almost everything about the electron. Okay? Everything about the electron including the energy. Now between classical mechanics and quantum mechanics, the only difference that we have between the two of them is the difference in operators. There are some operators in quantum mechanics which are not there in classical mechanics. But operators are just like the operators that you know classically, like plus, minus, multiplication and division. They are all operators. Similarly, there will be a few operators in quantum domain. Okay? And there is a very famous equation. Of course, I told you that I'll not bring in Schrodinger until much later, but I think it's time that we brought him in for a little while. The essence or the nutshell of the Schrodinger's equation is just this. H cap psi is equal to E psi. Okay? What is H cap? H cap is called as the Hamiltonian operator. Okay? When the Hamiltonian operator operates on the wave function, the Hamiltonian operator is called as the total energy operator. So it's like you have a wave function, you operate it with certain quantities, you get some output. Okay? Now, a better way to visualize this is, since quantum mechanics is difficult to visualize and to understand, there were two lines of thoughts which were simultaneously devised. One of them was devised by Heisenberg. Unfortunately, we don't hear of that too often. The only line of thought which we always come across is the Schrodinger's way of solving. You must have all heard about cat in a box and how the cat was put inside the box, it was rattled, particle in one-dimension box, particle in three-dimensional box and all those things, right? But we never really come across the Heisenberg way for solving. Remember that these two people, these two scientists developed the atomic structure simultaneously using two different concepts of mathematics. Heisenberg developed the atomic structure based on matrices. Matrices is something that we are much more familiar with, something which we associate with much better as compared to the wave or the quantum kind of domain, wherein you have the differentials of the wave functions, double differentials, d2 psi upon dx square, and partial differentials and so on and so forth. That was the line of thought that was devised by Schrodinger. Okay? What Heisenberg did was he only used matrices to be able to devise the true atomic picture and how the total energy of the electron is in an atom. Right? Now, how do you visualize this? Just visualize it as a vector. Okay? Say, for example, whenever you had a vector and you did some operation on the vector, you would always get a vector back and some scalar multiple of the vector. Isn't it? That is how it is. You have a vector, you multiply it by 2, you get 2 times the vector, but the vector still remains. You can visualize this statement just like that. You operate on a vector because psi is also a vector. It's also space dependent. It's not space independent. Okay? You operate on a vector, you will get back a scalar multiplied by the vector itself. It is just like that. Just try to visualize it in the same fashion. Okay? Now, there are many different operators in quantum mechanics. Let me not go to Hamiltonian. Let me show you another operator which you will associate with. E cap, which is called as the momentum operator. What will this do? When you operate a momentum operator on a wave function, it will give you the momentum of the wave function of the electron. Wherever there is a cap indicates an operator. Without the cap, this indicates a scalar quantity. So if you want to judge the momentum of an electron in that particular atom, you just operate a momentum operator on that wave function. What you will get back will be the momentum of the particle multiplied by the vector. And momentum, these are the properties that you want, right? You want the momentum, you want the velocity, you want the position. So for position, again, there will be a position operator. You can't just take the position because a wave does not have any position. So you will need to operate the position operator on the wave function to be able to get the position. In an s orbital, these infinite number of x's are plotted to get a spherical shape. That is how you get the shape of an orbital. Do you understand that? So just try to correlate it with your vector algebra, wherein you multiply something with the vector, you get a scalar multiple of the vector. That's all. That is all it is. One more definition that I want you to remember is that these values can either make sense or can be nonsensical. What do I mean by nonsensical? Root over minus 1 is a nonsense solution. Under root minus 1 is called as iota. Okay? Doesn't make iota of a difference to our problem at hand. And that is the reason you call them as nonsensical solutions. You can't plot them on a graph. You don't know what is root over -1. So such kind of quantities we leave out because they are not giving us real solutions. Any real solution like this is called as an eigenvalue. Because we can only work with real solutions, we only work with eigenvalues. I'm not saying that all solutions will be real. There will be certain solutions which will be real. There will be certain solutions which you will get for momentum which will not be real. So what do you do to the unreal solutions? You just discard them. And you take forward only those solutions which are real and you call them as eigenvalues for that particular electron. Do you understand that? So when you operate a Hamiltonian operator on the wave function, you get an eigenvalue E, which is the energy of the electron, multiplied by the vector, which is psi. Do you get that? And we'll come back to this time and again. Do we know psi for a H2 molecule? Do we know psi for the electron in an H2 molecule? No, we don't. We know it only for the hydrogen atom. We don't know it for the hydrogen molecule. So what do? We go on using approximate psis here. So what we get is approximate energy. Do you get what I'm trying to say? If we knew the exact wave function, we would have got the exact energy associated with the electron. Since we don't know the exact psi for a hydrogen molecule, we operate the Hamiltonian on, say, for example, psi1, some wave function psi1, which we have approximated using the variation principle. We will get, since I want to differentiate this eigenvalue from this one, I will use a Greek alphabet, epsilon. Okay? Rather than using E, I'll use epsilon multiplied by psi. Say, for example, if epsilon is coming to 10 kilojoules per mole, I'm just giving you a hypothetical value. This comes up to 10 kilojoules per mole. And actually the bond dissociation energy associated with hydrogen molecule is 478 kilojoules per mole. What would you say about your approximate wave function? Is it a good wave function or not a very good approximation? It's not a good approximation. Now you're being very good physicists actually. We've not yet come to the chemistry part of it. So that means there needs to be some more variations that you need to make to this one to better your wave function. Only then will your epsilon somewhat like closer. So what is our attempt? Our attempt is to make epsilon more and more close to the true value E. And for that we go on changing the wave function psi according to our variation principle. Is that absolutely clear? That is our basic aim when it comes to VBT for this molecule. Okay? Okay, now we've landed up to the first and foremost equation which two scientists started with. I'll come to the scientists a little later. So the first logical explanation is that the wave function of one of the electrons will go and interact with the wave function of the second electron of another atom, and you get the first wave function like this. Okay? When they calculated the energy based on this first wave function, they got a huge disparity between the value epsilon and E. What does that mean? These two terms do not do complete justice to the wave function of the electron in the H2 molecule. We know that for a fact. How do we know that? Remember that just looking at the wave function, you can't tell anything about whether the wave function is a good approximation or a bad approximation. When do you know whether it's a good or a bad approximation? When you put an operator in front of it, operate something, get an eigenvalue, only then will you be able to judge whether the wave function is accurate enough or not. So when we try to do a Hamiltonian of this composite wave function and try to get the eigenvalue epsilon, we see that there is a huge disparity between epsilon and E. So what does this mean? This means that there is some more modification required for this wave function, right? Now, what was the assumption that we started with? We started with the assumption that there is a hydrogen atom, there is another hydrogen atom, the hydrogen nucleus over here, and we said that the electron E1 is associated with HA, the electron E2 is associated with HP. Does that seem like a logical assumption to begin with? when the electrons are present around both the nuclei, there is a possibility that E2 can also be associated with HA. There is a possibility that E1 can also be associated with HB. So that means there is some innate limitation to this wave function that we have approximated. Okay. So what was the first improvement? Now these are improvements. There are 3 improvements which we will study. And at the end of the third improvement, you will see that the energy obtained after the third improvement is somewhat close to the true experimentally observed energy. That is when we will say that according to valence bond theory, we have conclusively built up the molecule of hydrogen. Is that clear? So what was the first improvement? First improvement was that this cannot be the true picture. So you should have 2 different wave functions. Let me say psi1, wherein, let me just, for simplicity, let me just omit H and write A. Assume that psi A refers to HA. Okay. 1 plus psi B 2. Okay. So you have one wave function which should be a product of the wave function wherein the electron 1 is associated with hydrogen A and electron 2 associated with hydrogen B. But there could also be an equal likelihood of psi 2 wherein the electron 2 is associated with hydrogen A and electron 1 is associated with hydrogen B. Are they both equally likely? They are both equally likely, right? So therefore I'm not going to put a weight factor in front of it. I'll come to that a little later. So I can now say that the total wave function should be psi 1 plus psi 2, right? It should just be a addition of the psi 1 which we've approximated as electron 1 associated with HA, 2 associated with HB, and psi 2 wherein electron 2 is associated with HA and electron 1 is associated with HB, right? Remember that whenever 2 waves interact with one another, there is a possibility that a crest and a trough can come together, or a crest and a crest can come together. So always remember, linear combinations are always additive as well as subtractive. So you can't just end at this. You should always have the total wave function as plus or minus that. Because you don't know whether the 2 troughs will come together or whether the trough and the crest will come together. So depending upon that, you could either have, so that's why we call them as linear combinations. And linear combinations are both additive as well as subtractive, right? So you have 2 different wave functions. One of them will be psi 1 plus psi 2 and the other one will be psi 1 minus psi 2, right? Now I'll retain this figure wherein this line which I've drawn is the true experimental value obtained for the H2 molecule. Okay. When we worked on the first equation, psi 1a plus psi 2b, we got the scientists obtained a graph like this. So huge disparity between the epsilon here and the true energy. Okay. So let me just call this as A. A is the true picture of the molecule when the 2 hydrogens are at equilibrium distance apart. And I got B when I worked on the first equation. Okay. Now for the first improvement, I should get 2 different lines. One line should correspond to psi 1 plus psi 2 and one line should correspond for psi 1 minus psi 2, right? The psi 1 plus psi 2 line gave some improvement. Of course, it's not to scale. Just to tell you that there was some improvement. Note 2 things. One is that the potential energy is less for the other graphs. At the same time, the energy minima is somewhat ahead. Can you see that? The energy minima here is pointing towards a bond length of so much. Whereas the energy minima for the true molecule is pointing to a bond length so much. Do you understand that? Because you can't have the 2 nuclei to be at the same internuclear distance but having a different potential energy. We can't have that. So if the potential energy is changing, it is obvious that the wave function is pointing us to a different bond length. Are you understanding that? So both these are going to be improved. The bond length is going to be improved as well as the energy of the molecule is going to be improved with each improvement on the wave function, right? So this happens to be C, so you get a minima over here, which is somewhat better, but still not good enough. So C corresponds to this psi 1 plus psi 2, which is often written as psi plus, because it is a constructive interference of the two wave functions psi 1 and psi 2. We call that as psi plus. Since this is a destructive interference of the two wave functions, we call this as psi minus, and its wave function is going to look like D. It is leading to a repulsive state. Can you see that? The potential energy is in fact greater than when the two atoms were separate. When you bring them closer together, the energy is becoming more. Higher the energy, less is the stability. So this is going to refer to a repulsive state. Now, how do you analyze this data? You have a hydrogen with a spin. We know that there is a spin quantum number. So if the spin quantum number of this hydrogen is plus half, say for example this hydrogen also comes with a spin state of plus half, there will be a repulsive state. So that D over there is referring to a violation of the Pauli's exclusion principle, which states that all the four quantum numbers, no two electrons can have the same set of all four quantum numbers, right? So when do you have an attractive state? When there is C actually, wherein one of the electrons is coming with one of the spin states, the other electron is coming with the other spin state, so that there can be some kind of an attractive state. Okay? Always remember, these wave functions will not make much sense, but we'll have to try and transform it into the chemistry that we know and try to correlate the two so as to better our understanding of these electrons. Okay? This one is the first equation which we started with, psi HA1 plus psi HB2, which gave us an extremely low value for epsilon. Okay, so that's the first curve. Then we started improving the wave. Which was the first improvement? We said that the electron need not be associated with HA. The second electron need not always be associated with HB. There will be exchange. So that brings us to another very important concept. This difference in energy between the first and the second curve is called as the exchange energy, for obvious reasons, because you have accounted for an exchange of electron between the two nuclei and therefore got a lowering in energy, and hence we call it as an exchange energy. But again, we are not doing very good so far. There is still so much to go. There's still some disparity in the bond length. There is still some disparity in the energy of the molecule. So we need to better the wave function further, right? So there is one more modification which was suggested. The first one, let me just write it down here so that it stays. First one is the exchange. The next one is based on shielding. Okay. Now what does this shielding mean? You have the two protons coming closer together. Okay. You assume that when the protons come closer together, there will be proton-proton repulsion, right? So that will not allow the two protons to come closer together, much closer together. It will hold the two protons further away. But what we are not accounting for is that there is an electron cloud that is somewhere in between these two protons. And they will shield this proton from coming into a repulsive state with the second proton, and hence you can bring the two protons more closer together. Did you follow that? For this we don't have any equation. We don't have any equation to tell us something about the shielding effect, but what exactly does the shielding effect do? The shielding effect allows for bringing the two protons even more closer together. And how does it do that? Because we know, according to our logic, that in the internuclear line, the line that the internuclear axis between the two nuclei, there has to be electron density. If there is an electron density in between these two, there is no repulsion between the two protons, and therefore the protons can be brought further closer together, and hence you will have another curve which will be slightly lower as compared to the one with the exchange energy. So which is the second improvement that was suggested? The second improvement that was suggested was that of shielding effect that comes up due to the electrons which are present in between the two nuclei, right? Still it was not good enough, so one more suggestion was made right at the end, which is the third improvement, which talks about ionicity. Okay, we've assumed that first hydrogen is associated with electron 1, the second hydrogen is associated with electron 2, or the other way around in the exchange fashion, right? But we've not yet accounted for a fact that there is also a possibility both the electrons at some point in time can lie on one of the atoms. There is a possibility like that because the electron cloud is just moving, right? Both the electrons can be associated with one of the atoms, or both the electrons can be associated with the other atom. So how exactly can you picture the molecule then? You could either have a pure covalent bond wherein the electrons are midway between the two, or you could have positive, negative. What does this mean? Here HA has one electron, HB has one electron. Here HA is associated with no electrons, HB is associated with both the electrons. You could have a third possibility wherein HA is associated with both the electrons and HB is associated with none. Well, I can't really show a bond because now it becomes like ionic bond, Na plus Cl minus, right? You don't draw NaCl with a line because line indicates a covalent bond. Here they are just electrostatic interactions between H plus, which is called as a proton, and H minus, which is called as a hydride. So we are accounting for ionicity in the bond. Remember that until recently we always could put compounds into two baskets, ionic compounds, covalent compounds. But now we know that there is some extent of covalent character in ionic compounds and there is some extent of ionic character in covalent compounds. So no bond is actually, so to say, purely covalent or purely ionic, right? So therefore the third improvement which was suggested was to account for ionicity of the bond. Note the use of double-headed arrows, which you will be coming across very, very often in your course on organic chemistry. Wherever you draw resonating structures, you always separate two resonating structures with a double-headed arrow. And that is a said rule. That is the way we write canonical forms. So in fact, you can also visualize these three structures to be three different canonical structures of the hydrogen molecule. One wherein it is perfectly covalent, one wherein there is some amount of ionicity, and the third one there is some amount of ionicity in the reverse fashion. Okay? If I have to put a value for wave function for both of them, psi A1, the proton A is associated with electron 1, the proton A is associated with electron 2. Which structure am I talking about? 1, 2 or 3? Psi 1 is for which one? Second structure, first structure. Psi A is associated with electron 1, psi A is associated with electron 2 as well. So which structure am I talking about? I am talking about the third structure wherein this HA has a negative charge. That means both the electrons are associated with the atom HA. So the wave function becomes psi A1, psi A2. Both electrons 1 and 2 are associated with the proton A. And when I am talking about psi 2, which structure am I talking about? I am talking about the second structure wherein both the electrons are associated with the hydrogen atom B. Is that clear? Again, they are both equally likely and therefore I should have a linear combination of the two. I should get, in fact, plus psi B1, psi B2. Right? A linear combination of the two. And this, I say, is the ionic term of the wave function. Now what do I need to do? I need to go on adding. First I had the exchange wave function. I take that wave function and call that as psi covalent. The entire term that was obtained after the exchange, I call that as psi covalent. And this term that I have obtained here, I call it as psi ionic. Do you follow that? After exchange, we got a wave function called psi A1, psi B2 plus psi A2, psi B1, right? that I call as the psi covalent, because it is accounting for covalent interactions between the two hydrogens. Here I call this as psi ionic. The total wave function should be psi covalent plus psi ionic, except that there is a small lambda which is introduced before the psi ionic. Can you tell me why? Is the psi covalent and psi ionic equally likely according to your concepts of chemistry? Is it equally likely for hydrogen to exist as H single bond H, or H plus H minus, or H minus H plus? Are all these structures equally likely? Which one is the most stable canonical form? Can you tell me? First one is the most stable. So that means the weightage to psi covalent should be the maximum, and the weight that you should give to psi ionic should be somewhat lesser. The experimentally observed, to tweak, to be able to minimize the energy, it was seen that to an extent of 0.14, where lambda is called as the mixing coefficient, and that coefficient came up to approximately 0.14. So you only have that much degree of ionicity. You can't have the ionic character and the covalent character happening with equal likelihood. Do you understand that? And this is what gave you the final line. Of course, the final line also stands quite clear of the actual, but this is the best we can do. Okay, and the best we could do gave us an energy of 388 kilojoules per mole for the hydrogen molecule. Still there is a disparity, 476 and 388, but this is the best we could do after 3 improvements on the wave function. The scientists who are involved are called as Hietler and London. Yeah, I'm done. So we are done with VBT. Next time we'll look at MOT.